Assalamu alaikum, I am Awais Akbar and today I am going to explain the C code and simulations of microcontrollers and embedded systems lab mid and finals. So let's have a look at the problem statement. We need to design a line following robot using three IR sensors. We need to attach a temperature sensor such as LM35 and display the readings of it on LCD. We need to control the speed of motor using PWM technique. We need to develop a hurdle detection system for the robot and display the warning in case there is. And we need to use serial communication to connect two microcontrollers together, and we need to display all the things on LCD using the second microcontroller. So these were the objectives. Coming to the things we'll use in Proteus simulation: LM35 temperature sensor, L298 motor controller, ultrasonic sensor. Instead of this, we'll use potentiometer in our Proteus simulation, because ultrasonic sensors works by emitting and transmitting the radiations. But in our case, we can't do this on simulation, so we have used a potentiometer. Same here, instead of three IR sensors, we have used three switches. Then we have used two microcontrollers, two motors, and LCD. Coming to flowchart, first of all we'll get the temperature reading and distance readings from respective sensors, and then this is the hurdle detection system. If the distance is greater than 20, then it will perform the next tasks. If no, then it will move back. How it works: if the hurdle is near, then the distance should be less than or equal to 20. So in that case, it won't go further. If there isn't any obstacle, then it will check for the following four conditions: that where our black line lies. For example, if the black line lies in the middle, or both the left and right sensors detected, then it need to move forward. And if the left and both left or middle sensor detects the black line, then obviously it needs to move left, and same for right. If the black line is detected by none of the sensors, then it needs to keep moving forward, and if it is detected by all the sensors, then it is a sign that it needs to stop. Then using serial communication, we need to show the temperature and distance reading on the LCD that is connected to the second microcontroller, and then it will start from here. This whole thing is in a while loop that is continuous without any condition. Block diagram. Here let's have a look how we have connected and where we have connected our components. We have used Arduino Uno, that is at Mega 328P microcontroller, and Arduino Mega at Mega 2560 microcontroller, and they are connected by serial communication. We just had to attach LCD to at Mega 328P, and all the sensors and motors, including ultrasonic sensor, LM35 temperature sensor, the three IR sensors for robot, the motor controller, and two motors, to Arduino Mega. Coming towards calculations, now we need to keep this thing in mind, that we have used a potentiometer instead of a distance sensor or ultrasonic sensor. So if we have used a potentiometer, that is mere assumption, so there isn't any formula for it. We derived this formula voltage divided by 20 as distance, as it looked right to us, but as I told before, there isn't any question of accuracy of it or not. So in our case, we are dividing the voltage by 20 in our code, and whatever the value is, that is being displayed as distance. Coming towards temperature, we have used LM35 temperature sensor there. in our Proteus simulation, whatever, as it cannot detect the temperature in Proteus, so what we have done is that whatever the reading we set for LM35, like the input of sensor is also being given by us. Whatever the reading we set for LM35, that is displayed on temperature. So after a few observations, we came to know that the voltage in millivolts need to be divided by 2.1 to get the temperature whatever we are giving to LM35, that to be displayed on the LCD. One more thing, as this reading will obviously be in float, but we are recording it in integers and then converting it to characters to be displayed to LCD. So sometimes, for example, if the reading is 2.9, when it will be converted to integer, it will show as 2. So you can add 1 here if you want to for accuracy, or sometimes that isn't even needed, so it's your choice. I haven't used it. Okay, so next calculation is for motor speed. Note that practically we use DC motors, but in simulation we have used encoder motors because they show real-time speed of motors. Formula for conversion is quite simple. PWM divided by 255. This is the prescaler. We have defined it as 256 prescaler, and 5 volt is the input voltage. So for 55 PWM, motor speed is 1.078. For 155, motor speed is 3.039 volts, and for 255 PWM, the motor speed is 5 volts. All these calculations are from this formula. So before going to code, let's quickly go through this Proteus simulation so we are familiar what's happening in the code. This is our Atmega 2560, that is Arduino Mega. Here is our robot. These three are switches that are acting as IR sensors, and these two motors that drive the wheels. Here we have LCD display, and our task was to control this LCD using Atmega 3280p while all the sensory work is being done by this Atmega 2560. Here we have two sensors, the temperature sensor and distance sensor. As I told you that distance sensor is our potentiometer here, and the temperature sensor LM35, we are inputting the readings here. Whatever we are giving it, that is to be displayed on the LCD. So actually it can't detect temperature here in the simulation, so we have to input the temperature as well and display that thing there. This is our Atmega 328p for serial communication. Here it is the motor controller. These motors need to be controlled using something, and we are using L298N. And here is the PWM. We have made it separate. I'll tell you when it's the turn. So let's move towards our code. First of all, we have defined the frequency of the crystal to 16 megahertz. Then we have included the input, output and LCD header file. Then we have declared three functions that we need to use. We'll have a look at these functions shortly. These two integers are to store distance and temperature respectively, and these temperature and distance characters do the same thing. Then why we have initialized both of them? The answer is that we get the reading in integers, but the LCD displays only in characters. So we need to get the reading in integers and then convert it to characters and give these characters to LCD so that it can display. Coming towards main function, here we have used 4 ports. The A port as input, The A port is used as input for sensors like IR sensor, and the other three ports are used as output. We'll be discussing them where they are being used. First of all, we have cleared the LCD. This is a command 0x01 to clear the LCD, and then we have initialized the LCD. LCD initialization is a function in header files. Let's have a look what's inside it. LCD initialization. First of all, it initializes the 16 by 2 LCD in 8-bit, then the same as we did there, clears the LCD screen, then turns on the cursor. Cursor is that blinking line that we see on our LCD, and then it moves the cursor to 0th position of first line. That was all inside the LCD initialization function. This is a while loop, the continuous loop without any condition, so it will keep on doing its work, whatever in it, until the program is stopped or simulation is stopped. First, this temp was the integer to store temperature, and we are storing whatever is being returned by get temperature function. Let's have a look what our get temperature function is. Okay, so here is our get temperature function. ADMux, analog to digital multiplexer. We are giving analog signal in voltage, and the sensor's output, we need it in integers, that is digital, so we need to use ADMux, analog to digital multiplexer. In the first step here, we have enabled the analog to digital multiplexer, and here in mux 0, mux 1 and mux 2, what we are doing, we are giving it a specific code 101. 101 in binary means 5, from binary to digital means 5, which means that we are selecting the pin ADC 5 to be used. Let's see it in our Proteus. Here we are using AD5 pin for our temperature sensor, and let's have a look at it. Here AD5 pin is connected to ADC5. So we were actually selecting the pin. In the next register, analog to digital control and status register, we have enabled the analog to digital, then we have enabled the analog to digital interrupt, then this is also a code ADPS2, analog to digital prescaler selection bits. So what is prescaler? 111. It is a code that means that we are selecting 1 to 8 prescaler. In the next step, the pin that we had selected ADC5, now we are enabling that pin to get the values. Here we have started the conversion from analog to digital. Whatever the thing was in analog, it is being converted into digital here. And what is this empty while loop? We haven't written anything inside it, so why is it here? This is the interrupt flag. The interrupt flag will remain 0 until the conversion is taking place. So we are waiting that until this interrupt flag is 0, this empty while loop will be processing. This is a preventionary step to avoid anything else happening while this conversion is taking place. We don't want anything else to happen, so this is kind of a delay. and this is then check a force flag. Actually we don't need this line because there is a while loop until the ADIF is high, it won't get out of it, but just as a precautionary step we have taken this. Then here in calculations I have discussed this, that this is the formula to convert the voltage in millivolts divided by 2.1, that will be our temperature, and then we are returning the output. That means that this whole function is returning this output, the conversion. So that temperature, whatever was being returned, that is stored in this integer. Next we have distance, get distance function. Let's have a look at get distance function. Here the same way, we have input as analog and we need output as digital, so we need to use ADMUX, analog to digital multiplexer. We are enabling the ADMUX, and here we are selecting the pins 0 0 0. This means 0 0 0 in binary is equivalent to 0 in digital. So this means that we are selecting ADC 0 pin. Let's check it in our Proteus. Here we are using AD0, which is connected to ADC0 of Arduino Mega. Then analog to digital control and status register, we are enabling the analog to digital, then we are enabling the interrupt, then we are setting the 1 to 8 prescaler. As I told you that this 111 is a code for 1 to 8 prescaler, and then we are enabling the ADC0 pin to get values. Here we have started the conversion, analog to digital start conversion. Here the same way, we are waiting for the interrupt flag to go high. The time it is low, the conversion is taking place and nothing else is happening because of this empty while loop. And then as a precautionary step, we have forcefully turned on the flag. This is the formula for ADC conversion discussed in that conversion thing. That this isn't something like a perfect formula that we got from somewhere. This is just like we felt okay with it, because everything is in assumption here. The important step, I guess that was step number 4 or what, it was to check for obstacles. So here this output is actually a distance, so we it was asked to us that we need to give the warning if there is an obstacle ahead. So if the distance is less than 20, this means that obstacle is near, so we need to display the warning obstacle head on LCD. Then give a delay of 500 milliseconds and then clear the LCD. And the important step, if there is an obstacle ahead, we don't want it to, our robot to collide with that obstacle, so we are turning the motors off. This 7-8 represents motor off. How? We are giving 0 0 0 to the motors, and this is returning the output. Let's go back to our main function. So that output was being stored in this integer. Now, as we discussed in the flowchart, if distance is greater than 20, then we need to set directions for it. What is set direction? Let's have a look at it as well. The condition is that if pin A is equal to 0x05 or 0x02, then port D needs to be this. So what this thing actually is, 0x05 represents 0000101. and 0x02 represents 1 only on the second bit. How does it work? Let's move towards Proteus. As I told you, our sensors are connected to port A and our motors are connected to port D. If I'm not wrong, let me recheck. Yeah, port A and port D. So this is the condition. Let's have a look at it in Proteus. First of all, we need to understand the pins, that what's happening here. These are our three sensors, the left, middle and right. Where is it connected to port A? In the power and control unit, we have placed IO22 to left, 23 to middle and 24 to right. This means that pin A0 to left, pin A1 to middle and A2 to right one. Now let's check what our condition is. Our condition states that black line on sides or black line in middle. 0x05 states 101, which means that this one is 1, this one is 0, this one is 1, and let's not have a look at all the others, we don't need them actually. So 101, this means that the middle one has a 0 value, and I have written it that 0 represents black line. Why 0 represents black line? You can change it actually according to your code, but when a signal is sent, the black line absorbs that signal and does not send back, so there is a 0 value, nothing going back to the receiver. So that's why by default we take 0 as black line. So this means that the black line is only in the middle. If the black line is in the middle, if that is the case, then this thing will happen, and there is a second case as well. Or if there is a black line on both the sides, let's see it as well. This is 0 1 0. Let's forget these bits for a moment now. 0 1 0. This means that black line on left one, nothing on middle one, and black line on right one. So in both these cases, what we are saying that we need to execute 0x28 command, which means move forward. How? For that we need to have a look at our robot, how our motors are connected. Our motors are connected from out 1 and out 3 to this motor controller. Both of the terminals are connected to motor controller out 1, 2 and out 3, 4. And how is this motor controller connected to the microcontroller? We have used the microcontroller pins PD3, PD4, PD5 and PD6 for this inputs. Now we can understand our code better. We are giving the command. Let's not think about the first 3 bits because we are starting from PD3. So let's not worry about PD0, 1 and 2. We are giving 1 0 1 0. What does it mean? Here from PD3 we are giving it on, off, on, off. We are giving here the combination from PD3 1 and 1. So we are actually turning on the IN1 and IN3 pins, which refer to both motors, the IN1 for first motor and IN3 for second motor. So we are actually asking or commanding both the motors to move in this case. Let's check our second case. If there is a black line on left or both left and mid, combination is 1 or 1 1. So if the combination is 1 or 1 1, black line on left or black line on both left and middle, then what we are saying is that the robot needs to turn left. How? 0x08, which means that the first one is on. We don't need to consider this. These three are useless in our case. So what we are actually doing is that we are turning on the in 1, which is IO18. We are turning on the in 1 and it is connected to out 1, which means that the left motor will be turned on. In the same case, if the black line is in the right or both the right and middle, so if the black line is only on the right one or both right and middle, then what it needs to do, execute this command 0x20. Let's see what's in here. This means that this pin will be turned on PD5, and we know that PD5 is connected to IN3, which means that the second motor will be turned on. So the second motor is the right one. So if there is a black line on right, it will move towards right. If there is black line nowhere, this means that all of these are 1. If there is a black line nowhere, then no, this is 1, this is 1, and this is 1. All three are 1. There is no black line. Then we need to give the robot 1010 condition, that you need to keep moving forward. The 1010 condition was given here in our first case, and we have checked that it is for moving forward. The next, if there is no black line, if all these sensors are off, then you need to turn on all of these, which means that the robot needs to stop. So we are turning on all of these off, which means that both of our motors will be stopped. This was our set direction function. Next, what we are doing, we are converting the temperature in integers to temperature in character to be displayed on LCD. Then the distance in integers to distance in characters to be displayed on LCD. Then we are showing these characters temp. This is not the temperature reading, this is just temp. And then after it, the temperature reading, clearing the LCD. Then we are showing dist and then the distance reading, and then clearing the LCD. That was all from the main code. Now it's turn for the PWM code. The PWM code, first of all, we are including the input, output and delay header files. Then we are defining a process to get bits. This define function is used to tell this Atmel Studio that this is what we are going to do in our program. So we have defined that you need to get this value and store it in this one. So this is simple a definition. Then our main function, the first line is declaring some pins as input and some as output. What is happening here? Let's see. 000 means that they are being declared as input, and 111 means as output. So why the first three as input? Let's see it in Proteus. In Proteus, if we have a look at port D, the first three pins P1, P2 and P3 are connected somewhere, and that somewhere is these three switches. So switches act as input, so that's why the first three were declared as input and the rest as output. We only need this PD6 as output, but that doesn't matter. We have declared all the rest as output. Here TCCR0 timer counter control register. What's happening in here? The COM registers. There are two COM registers, 1 and 0. And in our case, we have turned the first one as on, and if the second one is not turned on or off, this means by default it is off. So this is a combination. The 0-1 combination of COM refers to compare, clear on, compare, match. The second combination, WGM pins. We have 3 WGM pins, and these are used for PWM speed. We have turned on 1 and 0th pin, and the second one is by default off. So this means the combination is 110. The 110 combination refers to fast PWM. And second, we have turned on the first C chip select bit, CS bit, and the rest are by default 0, and this means there is no prescaling. So in this line, what we are doing, we are setting the mode to clear on, compare, match, setting the PWM to fast PWM, and no prescaling. That's what is happening in this line. Next, in the timer mask register, what we are doing is we are enabling the interrupt. This is IE, interrupt enable. In the second timer counter control register, we are setting the prescaler to 256. How? CS00 pin is 0 and CS01 is by default 0. CS02 is only 1. This means 001 combination, which refers to 256 prescaler. And this one 255, because it starts from 0, so we won't write 256. The 256th number will be 255. So this is also setting prescaling. This is a continuous while loop. Continuous while loop, as explained, as long as the program is running, the simulation is running, this will keep on moving. There are 3 conditions here. This is the actual speed here. By default we have set it to 255, but if the pin D is selected, this get bit, as I told you, there we have defined it. So if the first switch is on, the pin D0 is on, then what will it do? The speed will be 0. This means that our motor will stop. If the second switch is on, then almost the OCR0 is half. The 150, it will run at 150 speed, and if the third switch is pressed, then it will run at its maximum speed. The motor will run at 255, which is the maximum for 256 prescaler. Let's run this in our simulation and check whether it works or not. Wait, there are some errors. What is the error? This is fine. Okay, sorry for that. So we said that if we press the first button, then the motor will stop. So we have pressed the first button and the motor is slowing down and will eventually stop. For the second button, we said that the motor will run at approximately half speed. So it is running at about 21 or 22. Now it is gone to 23. So it will just remain here at half, 23 and 24. It isn't moving further. And if the third bit or the third button is on, then the motor will run at its maximum speed, that is approximately 40. Now coming towards a question, an important question, that I have connected the PWM to Atmega 3 to 8P and there is a separate motor, while our task was to control these motors using Atmega 2560 as from PWM. Then why I did this? The simple answer is that when we give a PWM signal to this motor controller, we need to control these motors from motor controller. So when the PWM signal is given to the motor controllers, that signal is neglected by this L298N. We tried doing different things, but it didn't work. So to show that we can do PWM, I have connected it to Atmega 3 to 8P, which was to be used for serial communication, and I have shown it that directly PWM, by directly attaching PWM to the motor, everything is working fine. But this L298N cannot be in between this microcontroller and motor for PWM. That's what I think. Now coming towards our overall simulation, let's see how this robot is working and all these things. This 5 volt and 12 volt and ground is the power unit, so we have attached them wherever needed. For example, in our motors, for example here we have attached 5 volt and ground. Instead of placing it again and again, we have just placed it once so that we can use it. Okay, so let's run the simulation and check our robot. In our first condition, remember 0 represents black line, 1 represents white surface. So the black line is in the middle. That was the first line of our code. If the black line is in the middle, then both the motors will have to move. And there was an OR condition. If middle is 1 and left and right both are 0, then the motors need to move as well. So let's do that condition as well. So here is the condition. If both the sensors are detecting the line, the simulation is a bit slow. So if both the sensors are detecting a black line, then in that case it has to move forward. Okay, so our second case was that what if the sensor is the left sensor detects a black line. So what do you say? If there is a black line detected by the left sensor, then obviously it has to move towards left, and for that the left motor needs to stop and right motor needs to continue. So let's check that condition. Let me turn on the right, which means that there is a white surface under right. Now only the left sensor detects a black surface. So you can see that the left motor is slowing down and the right motor is continuing, which means that it is turning towards left. And if we even turn the middle sensor, it would have no effect because the condition remains same. Let's try it out. There's no effect, of course. Okay, case number 3. If we have black line under right sensor or both right and middle, then what will happen? Let's see. Let's turn it on, and the right sensor detects, right and middle both sensors detect the black line. So right sensor, right motor needs to slow down, and the left motor needs to rotate so that the robot can turn left, and yeah, that's happening. The right motor has stopped and left motor is continuing. Even if we turn on the middle sensor, which means that the white surface, the condition remains the same. Yeah, things are same. Now there was a third condition which states that there is a white surface under all the sensors. Then what will happen? Let's check that condition. Under that condition, both the motors need to keep rotating and the robot needs to move forward. And yes, both the motors have started. This was our case number 4. Now the last case. If there is a black line under all the sensors, you can see in RoboLine Arena, for a robot to stop there is a black line placed, a strip that is perpendicular to the line in which the robot is moving. Why is that placed? That black line means that now all the motors need to stop. So let's make that condition. There is a black line under all the 3 sensors. Now both the motors need to stop. And yeah, both the motors have stopped. So that was our condition for RoboLine. It's working fine. Let's check the problem statement once again to see what's left. First task completed. Second task, use LM35 temperature sensor and display the reading on LCD. Let's do it. As I told you that we'll input the reading here, so we have set it to 40 and the distance and the temperature that is being displayed here is 39, which is approximately 40. As I told you, it is not precise because it was our own calculation. It can be a bit inaccurate, but approximately 39 and 40 are close. Let's change it and see whether it works. I've set it to 65. It will take some time here to be displayed. It will display 46. The next time it will display something near. Temperature 63. Now as you can see that it is increasing. Okay. Our task number 3 was to control PWM, to control motor using PWM. That has been done. Fourth task was hurdle detection system. So as you can see that here in potentiometer I have set it to 25%, which is quite low. So it is showing obstacle ahead. It is displaying the distance and also giving the warning of obstacle ahead, and the motors are stopped. Let's check it. For example, in the condition middle is on. Sorry, yeah. The left and right sensors are on and the middle is off. By off mean white surface. So our motors should have moved, but they aren't. This means that our hurdle detection system is working perfectly fine. Now let's see by increasing the voltage a bit. Now it is 35. Let's take it to 59%. Okay. Wait for the distance to be shown now. Now it is showing distance as 17 and no obstacle ahead warning, and the motors are running fine. So that was our task number 4. The task number 5 was that this LCD should have been controlled by this at mega 3 to 8p using serial communication. Now as far as the individual task is concerned, I have done it in lab number 6 using SPI UART and I2C, all the techniques. Here is the simulation of it. For example, 9 is being displayed there from this microcontroller, and the LCD is connected to this microcontroller. 4 is being displayed there, 3 is being displayed. This thing is working fine here, but when I tried to integrate it to this system, it didn't work. Maybe due to the difference of microcontrollers, it is 2560 and this one is 328p, or maybe due to excessive code, because here in lab number 6 all we had to do was simple this task, but here there were many other tasks as well, so maybe due to that thing. But lab task number 5 was unsuccessful in this case, but it was done individually. So that's all for today. Thank you and Allah Hafiz.